Hey, good morning. Today, on Wednesday of this week, the computer system wasn't working, so I could not record the lecture. So I've come in, today is actually Thursday morning, the next day on October 3rd. I've come in to repeat the lecture for people who missed class or wanted to review what was said. Empty classroom, just coming in here early in the morning before everybody's here. So let us begin. First of all, there is homework that is due on Friday. Not this Friday, but a week from Friday, October 11th, over Chapter 4. So you want to begin to work on that this weekend so you can bring questions in next week. One thing we did on Wednesday is return the exams. I have the exams. If you haven't gotten yours back, stop by and get it. What I want to do today is I want to start talking about Chapter 4 and one of the problems at the end of the chapter, problem 4.19. And this is really about heat conduction. So we're going to continue really with the theme from Chapter 3 of thermodynamics, but I'm going to bring it in to heat conduction. So what I want to do is I start out considering a slab of tissue. You can think of it as tissue, or you can think of it as just a plane of glass. And I want to try to examine how the heat's moving through this. So X direction is going along in this direction. It has an area, cross-sectional area A. It has a thickness delta X. And over here, it's a cold temperature. So say this is a pane of glass, and that's cold outside on a winter day. And on this side, hot temperature. So, how much energy per unit time passes through this tissue or this plane of glass or whatever it is? Well, we're going to have a certain amount of energy per unit time. And first of all, it's going from energy or heat is going from hot to cold. So it's going in this direction. Positive X direction is this direction, so we need a minus sign. Then let's leave a little space. The amount of heat is going to be proportional to area. More area, more heat transfer. So we'll have an area. The amount of heat transfer is going to depend on the temperature difference. So we're going to define delta T equals T hot minus T cold. And you're going to find this is proportional to delta T. Also, if you make a very, very thin window, you'll get more heat transfer. Thicker window, you'll get less. So you're going to have divided by here a delta X, the thickness. Finally, there's going to be a constant proportionality in front of this. And we're going to call that kappa, Greek letter kappa, which is the thermal conductivity. And that specifies what type of material you have and how efficient it is in transferring heat. So, what are the units of thermal conductivity? Well, it has to give us energy per unit time, so it has to give us watts. But we're going to multiply by area, so it's going to have a meter squared. We're going to multiply by delta T, so it needs to have a degree C, or Kelvin. Since it's a change in temperature, it doesn't matter which. And we're going to divide by delta X, so a meter. So a watt per meter degree C is the units of thermal conductivity. Now, I want to define what's known as a heat current density. Heat current density. And this is going to be very similar to a molecular current density, or probably the most common one, a charge current density in when you're talking about electricity. So the heat current density is going to be the amount of heat per unit time per unit area. So all we got to do is divide through by the area. So we're going to define that as J. So in other words, J is delta E for delta T A. And that's going to equal minus kappa. And what's left is delta T, delta X. I want to go to the limit of small delta X, so this becomes a derivative. D temperature, dx. And what you have here is now a relationship between how well heat transfers through the material, temperature gradient. This is often known as Fick's first law. It's going to be one of our major results. Okay. It's often useful when we're talking about the thermal conductivity to look at the thermal conductivity of different materials. So let's make a little table. of the thermal conductivity. Remember, watts per degree C meter. And first of all, let's look at air. Air is one of the substances we live in. 0.026 watts per degree centimeter meter. That's a very low thermal conductivity. Air is a great thermal insulator. As opposed to water, we're always comparing air and water. Water is at 0.6. So water transfers heat much more efficiently. You lose heat if you're in the swimming pool much better than if you're lying around on the side of the pool. But even water is not that great. If you compare it to, say, a metal like silver has a thermal conductivity of about 400. So if you're comparing it to a really good thermal conductivity, and even water isn't that great of a conductor, but it's not bad. Okay, so there is part of our analysis. We're looking at, I'm going to write the final result, Fick's first law, way over here. J equals minus kappa dt dx. And then I'm going to have to get some more space. So I'll erase this. Now what I want to do is I want to look at a continuity law, really to see a little bit more about how this heat current density transfers through materials. So suppose you have a certain amount of heat moving from left to right, coming in like this, J of x. So this is x at this side, and this is x plus delta x, a little bit over along the other side, the right side. And now suppose there's a different amount of heat coming out of this side. Well, how could that be? Well, heat energy is conserved, so you think that the same amount of heat has to be coming in and coming out. But if this was tissue, you could actually have heat being created inside the slab. It has a metabolism. So it's possible, if you have a source of heat, to have more heat coming out one side than the other. So let's calculate now how, I'm going to go to the derivative, dE dt, the rate of heat, it's going to be the rate of heat that's building up inside this slab. So we're going to take this slab, we're going to look what's coming in, coming out, figure out what's the rate of heat building up inside. Well, there's heat coming in from the left, which is, this is a heat current density, and this heat per unit time per unit area. If we really want the heat per unit time, we have to go J of x times the area. That's how much heat's coming in from the left. You have heat going out on the right. You get a minus sign because it's going out. J of x is at x plus delta x because it's over a little further to the side, times the area again. And you have a certain metabolism going on in the tissue. Well, R star is the specific metabolic rate, the amount of heat produced per unit mass. If we don't want to do it per unit mass, but we want to do it per unit volume, well, we have to use the density. So the mass, heat produced per unit mass times the mass. The mass is the density times the volume, and the volume is area times thickness, A delta x. Okay, now let's go back and get one more idea from chapter 3, specific heat. If we want to know how the temperature of this tissue is changing with time, we have to look at how much heat's building up. We can relate it, heat increase to a temperature increase. So this is basically heat capacity times the change in temperature with respect to time. So the heat capacity is going to be the specific heat capacity times the mass, which is rho A delta x. That whole quantity right there is the heat capacity of that slab. And then this gets multiplied by dt, d little t. So what you've really changed is dE, the heat capacity, times dt, just like we talked a few days ago. That's equal to, well, first of all, I want to switch the order of these terms. I'm going to put this term first. I'll factor out a minus sign. So I'll get a j x plus delta x. And then I'll have this term, which now comes second. I factored out a minus sign, so I have to put a minus sign in here, j of x. And then there's going to be a that I'll factor out. And there's going to be then plus R star rho density A delta X. Now, at this point, I want to get a differential equation. It's just for d capital T dt. So I'll divide through by C star rho A delta X. So dt v little t equals minus. Okay, I'm going to divide through by, well, there's the A, that'll cancel that A. I'll get a C star rho. And then this thing will become J x plus delta X minus J of X divided by, and there's the delta X that comes down, plus, okay, rho A delta X is going to cancel rho A delta X. You're going to be left with R star over C star. Now, one more step. Realize that this is the derivative. As delta x goes to 0, that's the definition of the derivative. I need to be a little careful here. Temperature is now a function of both time and space, t and x. So really, I should be using partial derivatives. That is, I'll write the time derivative not as dt, but as a partial of temperature with respect to time, where that's the partial derivative symbol. It's just a fancy way of writing d as a partial derivative. All that means is if I want to take a derivative, if I knew what the temperature was as a function of x and t, I would hold x constant, I'd take the derivative with respect to t. We're not going to do much with partial derivatives, just want to realize, it's just a way of reminding you that we have two variables involved. Okay, and this is going to be minus 1 over C star rho, and this is now partial of J with respect to X plus R star over C star. Okay, this is another one of our big results. So this is one big result. This is another sort of a continuity equation. Problem is that both of these equations have both a T and a J in them. What we really like to do is get a single differential equation that just has temperature. So we can do that by taking the J here, this expression for J, and plugging it in right there. Let's see what we get. Well, this side doesn't change. Partial of temperature with respect to time is equal to. Well, there's a minus sign here and a minus sign here. They'll cancel. You have a kappa here and a 1 over C star rho here. So 1, a kappa over C star rho. Now you have a derivative here with respect to x, and really a partial derivative here with respect to x. Two derivatives, so you get a second derivative with respect to temperature. Very important. And then plus R star over C star. I'm going to put this result in a box, because this is our main result for today. This is the heat equation. What it says is a first derivative in temperature, in time, of temperature with respect to time, is equal to a second derivative of temperature with respect to x, plus the constant term representing the metabolism. Sometimes you see this called fixed second law. I'll call it really the heat equation. It's a combination of fixed first law relating the current density to the temperature gradient, and this, which I'll call a continuity equation, really conservation of energy. Energy coming in one side has to go out the other, or else being produced within the tissue. All right, now let us look at a little more detail at what's going on with this equation. When you have an equation that's that complicated, you want to look at different special cases to try to get some intuitive feeling of what's going on. So first special case is when it's uniform in x. Well, if an equation is uniform in x, it doesn't depend on x, then derivatives of x are going to be 0. What it really means if it's uniform in x is this term goes away. And now we can use a total derivative because it doesn't depend on x. The change in temperature with respect to time is really R star over C star. And that's exactly what we were seeing in a previous class when we looked at when we first looked at heat capacity, and we were, say, wrapping a person up in a thermal blanket, not letting him lose any heat, trying to see how his temperature, body temperature changed because of metabolism. We had that exact equation. So you've seen that before. So it's good that this reduces to what we've seen before in that special case. Now, let's look at another case. Suppose you're not dealing with biological tissue. Suppose this is just a pane of glass or some other non-biological tissue. In that case, there's no metabolism. There's no source of heat. R star is 0. And what you have now is time derivative. So you still have partial derivatives of the temperature with respect to time equals, and often we'll write this quantity as just a single variable, usually given the symbol big V, and then d squared temperature with respect to x squared, and no additional term. And if you want to just record what d is, it would be kappa over c star rho. That is the diffusion constant. This is known as the diffusion equation. It's the diffusion equation with a diffusion constant that's given in terms of the thermal conductivity, the specific heat capacity, and the density. So our equation just reduces to one of the most famous equations in physics, and it's an equation that will not only govern heat transfer, but also govern how particles and how molecules diffuse around in space, which we'll talk about on Friday. Okay, one other special case. Well, before we go to one other special case, what I'd really like to do is I'd like to compare the diffusion constant for air and for water, because we always like to compare air and water. So, for air, well, kappa, the thermal conductivity of kappa, we wrote down earlier 0.026, and that was watts, or which is a joule per second meter degree C. That's the numerator. The denominator is C star for air. When we talked about heat capacity, we found that air had a heat capacity of 1,000 joules per kilogram and degree C. Get out my glasses. And also, we have a density. Air is not very dense. 1.2 kilograms per meters cubed. Do the calculation. Let's see what happens. The joules cancel, the kilograms cancel, the degrees C's cancel. You get a meters cubed down here, which comes up, and that cancels one of the meters, so you have meters squared over second. You do the calculation, you get 22 times 10 to the minus 6 meters squared over second. Now, the diffusion constant always has units of meters squared over second. You can actually see that from the diffusion equation. This is a time derivative. Derivatives have units. 1 over second is a space derivative. 2 derivatives, so 1 over meters squared. So D has to have meters squared over seconds in order for the units to even work out. Now, is this a big diffusion constant or little? Well, it doesn't make a whole lot of sense to talk about it in isolation. What you really want to do is compare that to another diffusion constant and say which one's bigger. So let's look at water, our other major material for life. And water, we said, had a diffusion thermal conductivity higher than the air, 0.6, and it's got a large specific heat capacity, 4218, and a much larger density, 1,000 kilograms per meters cubed. So even though the thermal conductivity is larger, the density and the larger specific heat went out, and you have a smaller 0.14 times 10 to the minus 6 meters squared per second, a smaller diffusion constant for heat. So that says even though water has the larger thermal conductivity, it has a smaller diffusion constant. And that's because even though heat can transfer through water, not very easily because of the low thermal conductivity, it takes a lot of heat in order to raise the temperature. So in air, you may have a hard time transferring heat, but just a little transfer of heat will be effective at raising the temperature quite a bit. And that's what leads to the larger diffusion constant for air. So diffusion constant, thermal conductivity are somewhat different concepts you want to keep in mind. Okay, one other special case is steady state. Steady state means no change with time. Things are constant in time. If we have no changes in time, the time derivative is going to be 0. So then we're left with these terms. We can see that we have 0 equals kappa over c star rho d squared. I can use total derivative now because it doesn't depend on time, plus r star over c star. You can multiply through by the c star because that is in both terms. And I can bring this over and I can write it as d squared temperature with respect to x squared equals, I get a minus sign when I bring it over, and I'm left with an r star and rho over kappa, which is essentially a constant if we assume that these properties of the tissue are constant throughout. And what we have is now a differential equation just for x that tells us how to calculate the steady state heat temperature distribution. Steady state's important because, for instance, our bodies are very close to steady state in temperature. We are warm-blooded, but more importantly, we have a constant temperature of 37 degrees. So we ought to be able to analyze our temperature distribution using a steady state equation, unless we're heating up, spiking a fever, recovering from a fever, something like that. In that case, we wouldn't be able to make this assumption. But steady state assumption will be important. Okay. Let us now go on and look at a special case. So I'm going to erase this, and then we'll move on. I'm going to save this equation because we're going to look at a case of steady state. So we're going to need this. Dx squared equals r minus r star rho over kappa. Now, what I want to do next is I want to look at problem 4.36 from the book. Not the problem in your homework, but it's an important problem. What we're trying to do is we're analyzing the steady state heat distribution inside an animal. And the problem actually asks you to analyze this for a sphere, but we're going to do an even simpler case. We're going to analyze it for just a one-dimensional slab. We're going to do the one-dimensional version of this. So physicists will often say approximate a cow as a sphere, but we're not even doing that. We're approximating a cow as just a slab of tissue. So it's kind of a gross approximation, but the main theme of this class is to develop mathematical models, simple models that you can get information out of and then refine and become more realistic. So we have an equation for the steady state heat distribution. We also have a boundary condition. We're going to say that at the surface of this animal, the temperature is going to equal the temperature of the surroundings. So let's just draw this here. This is going to be a function of x position. We're going to say the animal has a thickness really of 2L. So it goes from 0 to L and minus L. So all this area in here is tissue. Tissue with a metabolic rate R star, with a density rho, and with a thermal conductivity kappa. And this is temperature. We're going to really be plotting temperature as a function of x. So outside here, we're going to have a surrounding temperature, which is basically uniform. That's the air outside, or the water if this is a animal that lived in water. Temperature of the surroundings, we'll assume is uniform, and we're trying to find the temperature distribution inside the animal. Okay, and our boundary condition then is that the temperature, so T of x is the temperature distribution inside the animal. And we know that at its surface, the temperature at the animal is the same as the temperature of the surroundings. So that would be a boundary condition. In the past, we have used initial conditions, temperature at initial time. Now when we're dealing with space, we're going to call them boundary conditions, the temperature at a particular unit, spatial plot. And technically, this would be plus or minus because it's the same boundary condition on both ends. All right, what's my favorite way of solving these differential equations? I'm going to guess a solution and check it and see if it works. So we need a solution that when you take two derivatives of it, gives you a constant, because this is basically a constant. These parameters, I'm assuming, don't change with x. So what function, when you take two derivatives of it, gives you a constant? Well, x squared is a function that does that. So we'll guess some constant, unknown constant a times x squared. You can also have a function that depends linearly on x, just b times x. We could add that in because if you had a function that was linear in x and you took two derivatives, you'd get 0, so it wouldn't screw up your equation. The problem is that this model for our animal is perfectly symmetric. It looks exactly on the same on the right as on the left. Our boundary conditions are symmetric, our differential equation is symmetric, the whole geometry is symmetric. So you expect that you're going to have an even function, same on the left as on the right. X is an odd function. It's different. The value on the right is negative the value on the left. Therefore, we don't expect to have any term like bx. We could add in bx and we could go through all the boundary conditions, and we apply the boundary conditions at both the left and the right sides, we find that b was going to go to 0. I'm going to skip that. I'm just going to ignore a bx term from symmetry. But you could have a constant, because the constant, take two derivatives, is going to be 0, so that wouldn't screw up your equation. So our guess will be ax squared plus c. Now, what do we do with the guess? We plug it back into the differential equation, and we see what we get. Well, if you take two derivatives of this, x squared, the first derivative gives you 2x, the second derivative just gives you 2. So the second derivative is 2a. That comes from taking this, plugging it in here. C gives you nothing when you differentiate it. Ax squared gives you 2a. Equals minus r star from the metabolism, density over thermal conductivity. Or in other words, A equals minus r star rho over 2 kappa. All right, we've already got A. If we only had two unknown constants, we have 1. But we've got nothing left else to figure out C. The differential equation doesn't tell us C. So what we can do next is we can use our boundary condition. So T at x is equal to, I'll just write down what I have for A, minus r star rho over 2 kappa x squared plus c. So far, all I did was substitute in what we have for A. And now, we can either do the left or right side. Because we assumed it's a even function, we can actually just do the right side. And so we're going to put in T of L, when x is equal to L, the temperature should be equal to T surroundings. So what's the temperature at x equals to L? Well, we just replace x by L. We get minus r star rho over 2 kappa L squared plus c. And this tells us then that C, I'm going to put it way down here, C is equal to T surroundings minus, and then is a plus, because this will come to the other side, r star rho over 2 kappa L squared. And we have A and C. So we've solved now for our general equation. We can write down a final expression for the temperature distribution. It's going to be this with C given by this. So we'll have T surroundings, that's from the C, This term has an r star rho over 2 kappa, so does this term. So we'll factor those out. Plus r star rho over 2 kappa. The term with c is plus L squared. The term with x is minus x squared. So we'll get L squared minus x squared. And that is our temperature distribution. In particular, if you want to ask what's the temperature at the center of this animal, where it's going to be warmest, we can just set x equals to 0. So the center of the animal, the temperature is the T surroundings plus r star rho over 2 kappa L squared. Now, let us think about what this solution means. Let's plot the temperature distribution throughout the animal. L, which is the x-axis, minus L. And we're plotting temperature as a function of x. Well, first of all, outside the animal, it's at T surroundings. So it's looking like that and like that. We assume outside the animal, it's a uniform temperature. Inside, it's this function. Now look, if you set x equal to L, you'll get L squared minus L squared. This term will go away and you'll just get T surrounding. It's a continuous function. That's good. We set it out. That was our boundary condition. That means we haven't made a mistake. If we have, we need a little space here. I should have put this down lower, but I'll have to do it like this. At the center, it's going to be T surroundings plus a term, r star rho 2 kappa L squared. And that's what it's going to be right here at the center. We calculated that. In between those two limits, it's going to obey this function, which is basically a parabola, an x squared function. It's an upside down parabola because of the minus sign. So it's a parabolic distribution. So our temperature distribution looks like this. It's going to be warmest in the middle, and then the temperature is going to fall off, and it's going to equal the surrounding temperature at the edges. Now let's try to see if we can look at this a little more specifically. Let's assume that this is a rabbit. Okay, so what values of these parameters do we have for a rabbit? Well, first of all, the size. How big is a rabbit? Rabbit's maybe like this. Diameter of maybe 10 centimeters, tenth of a meter. And L is really half of that. So L is going to be 0.05 meters for our rabbit. Specific, the metabolic rate is going to be R star. Well, we know that metabolic rate goes up for smaller animals. We could go back to chapter 2 and we could estimate what the proper specific metabolic rate is for a small rabbit. And we would get about 2.5 watts per kilogram. The thermal conductivity. Well, the rabbit's mostly water, so it's going to have the thermal conductivity amount of water, 0.6 watts per meter degree C. And the density. Again, it's mostly water, so it's going to have the density of water, 1,000 kilograms per meters cubed. So, if we want to calculate the temperature at the center, it's going to be the temperature at the surroundings plus R star 2.5 times 1,000 divided by 2 times 0.6 times 0.05 meters squared. So, 2.5 watts per meter degree C times rho, 1,000 kilograms per meters cubed times 2 kappa, 0.6 watts per meter degree C times 0.05 meters squared. All right, so it's a little confusing to me. 2.5. So I wrote the wrong units down for R star. That's the problem. R 2.5 is the metabolic rate. Metabolic rate should have units of watts per kilogram. Good. Example. This is an example where units are your friend. I looked at that and I immediately saw the temperature, the way I had it, the degrees C was going to cancel out, but that can't be, so I had to work out and figure out how I had my units wrong. Okay, kilograms cancel, watts cancel, meters, here's a meters cubed, here's a meter squared, and a meter in the denominator, they all cancel. And what you're left with is degrees C. So you're going to get T surroundings plus, and this works out to be 5.2 degrees Celsius. Well, that's kind of a problem, especially if you're up in the Arctic where it's a cold day outside, say freezing. And if you're outside, that means the center of this rabbit is only 5.2 degrees above the surroundings. But we know that the rabbit's a mammal. It should have like about a 37 degrees Celsius temperature at its center. So it looks to us like this simple model, while it's reasonable, doesn't really explain what the temperature is inside the rabbit. It might work for a larger animal where L was bigger, but for a small rabbit, it doesn't seem to work. Well, what's different about a rabbit up near the Arctic and the rabbit in our model? It's the fur. A rabbit up in the Arctic has a layer of fur over its body. What I want to do next is to analyze a somewhat more complicated model. So this is typical of our modeling exercises. Make a real simple model, analyze it, learn something, but also see its limitations, revise the model, make it more complicated. This revised model is going to be a little bit more difficult than probably what you'd see on an exam, but I wanted you to see it as just an example of how we can improve our models and make them more realistic. So I'm going to erase all this, and we're going to analyze the rabbit with fur. Okay. We're going to go through this rather quickly. What we're going to do is we're going to put a layer of fur on this animal. So at L plus delta, so the thickness of the fur layer is delta, you now have fur. And we're going to make sure that this model remains to be an even model, symmetric left and right. So at minus L minus delta, we also have fur. The fur has no metabolic rate, it has its own thermal conductivity. I'll call it kappa fur. And it has its own density. Okay. And what we want to do now is we want to analyze the temperature distribution. Well, in the tissue, we have the equation we had before. B squared T dx squared. It's the steady state temperature distribution that we got from the heat equation, equals minus rho, and I'm just going to use R star over kappa. Rho and kappa, that's for the tissue. And that is for the tissue, which is minus L less than X less than L. But in the fur, what's the situation? Well, you have the same equation, except the fur has no metabolic rate. Hair doesn't produce heat. So R star for the fur is really 0. You can write that as R star equals to 0 in the fur. And that kills off that whole term. So you just have the second derivative of the temperature is going to equal 0 in the fur. And that's going to really be for L is less than X is less than L plus delta. And the same thing on the other side. Now, we also are going to have boundary conditions, and we're going to analyze the boundary conditions in a few minutes. But let's go ahead and analyze and make a guess for the solution, analyze what we get from the differential equation. So our guess is going to be T of X. Well, there's going to be two cases. In the tissue, we have exactly the same situation we had for the rabbit without fur. We're going to make exactly the same guess. A x squared plus c. For the fur, things get a little more complicated. We're going to have no term with x squared because you're supposed to take two derivatives of it and get 0. If you had two derivatives of this term, a term like this, you'd get a constant. So we don't have the x squared term. But we could have a linear term that could actually go as the absolute value of x. So I'm going to write b absolute value of x. That is, you can have a fall off here, which is opposite of the fall off here. You couldn't have absolute value of x in the interior, because then you would have had a discontinuity in the temperature right here at the origin. That wouldn't have made sense. But since the fur never goes to the origin, we can have this linear term plus, and you can have a constant I'll call b. So now we have 4 unknown constants that we have in our model. So the price we pay for a more complicated and realistic model is more unknowns. So in the tissue, we can do exactly what we did before. And we can plug this into here, and I won't go through all that. That will give us A, the same as before, minus R star rho over 2 kappa. But that's all we get, because when we plug, the C goes away when we take the derivatives. We plug this equation, bx. If I only look over here, remember this is an even function, so I'll just worry about positive values of x. If we put our function bx plus d into this equation, it's satisfied no matter what b and d are. So we're left now with 3 unknowns, b, c, and d, and only one unknown's figured out. So we have to start applying our boundary conditions. Okay, one of the boundary conditions is going to be at the surface of the animal, the outside of the fur. So that's L plus delta, out here. There, the temperature is equal to the T surroundings. That'll give us one more condition, but we still have a couple more conditions. And this is where it gets a little complicated. We have internal boundaries that we have to match up. So one of the conditions, and this is the part that you probably wouldn't have been able to guess unless you have done these types of problems, is x equals to L. The temperature has to be continuous. The temperature has to be continuous. You can't have a large temperature gap between the surface of the skin and the fur. We're assuming there's no thermal layer there, thermal barrier. So you have to have a smooth temperature distribution. Otherwise, you have a discontinuity in the temperature, in which case you have a huge, gigantic thermal heat current, and that doesn't make sense. And also, one more thing is you can have heat coming in one side and going out the other of the surface. The surface itself is just a very, very thin layer. You don't have negligible amount of metabolic metabolism going on just right at the surface. So really at the surface, you have to have the heat current also be continuous. So at x equals to A, that J is continuous, which means minus kappa dt dx has to be continuous. Now we have 3 conditions to get our 3 unknowns. Let's see what these conditions give us. At x equal to L plus delta L, so we got to use this equation. I'm just going to forget the absolute values because I'm worrying about here at positive x for the moment. We get b times x. X is L plus delta equals to, or plus d, because we have a d here, equals T surroundings. Okay, that is this condition. At x equals to L, the temperature has to be continuous. So that means at x equals to L, this equation has to equal this equation. So we get A, which we know, L squared plus C equals B L plus D. That'll ensure the temperature is a continuous function. Finally, we have kappa dt dx has to be continuous at x equals to L. So take the derivative with respect to x of this function, we get 2ax. And we're evaluating x equals to L, 2al, and the derivative c is 0. And then we multiply it by kappa. In this case, we're inside, so that is kappa, the thermal conductivity, equals what? It's the derivative of this function evaluated to L. Well, again, d will give you 0 when we take the derivative. We take the derivative of x, we just get b. b times kappa. And the kappa would in this case be kappa in the fur. Technically, we have a minus sign on both sides, but those will cancel. Now we have three conditions. We already know what A is. We have three equations, linear equations for A, B, and C, and we can solve those. It's kind of tedious to just watch me do math, so I'm just going to state the solutions. You can solve three equations, three unknowns after class. You verify these are correct. We can start with here. We know what A is. A is this complicated expression, so we plug that in. We just have an equation for B. And we get B is equal to, A had a minus sign, so we'll end up minus rho R star over, kappa fur times L. Then we can plug that B into here and solve for D. And we can figure out what D is. D is going to be T surroundings, or T in the air, rho R star over kappa for L plus delta. And now we know what B and D, and we already know A, so we can come and solve this for C, and we can get an expression for C. And C is kind of complicated. C is T surroundings plus rho R star L squared over 2 kappa 1 plus 2 kappa over kappa for delta over L. And we've done it. We can write down the entire solution for the temperature distribution in terms of these. We know what these unknown parameters are. We can solve for the temperature. We have figured out the temperature inside the rabbit with fur. I'd like to figure out what the temperature is at the center of the rabbit. At the center means we should be using this equation, because this is the equation that applies from minus L to L. So we'll set x equals to 0, which means this term with A goes away. And the temperature at the center of the rabbit is just C. So this is, the temperature at the center of the rabbit is just here. Temperature at the center is equal to the same as C. And I'm just going to write it as plus, copy it down, R star L squared over 2 kappa 1 plus 2 kappa over kappa for delta over L. All right. Let's think about this now. Let's just see if this makes sense. First of all, if we took our model for fur, and we made the fur layer so thin that it was essentially 0, we ought to get what we got before. Well, if you make delta equal to 0, that wipes out this term. The parentheses just gives you 1. You get exactly the answer we had when the animal had no fur. That's good. It makes sense. If we take the, if we want to look at the difference between with and without fur, we really notice that this term is 1 plus this. This is the extra term. It's the correction factor that tells you the effect of the fur. Because if the correction factor was 0, you'd have exactly what we had for the animal without fur. So we really want to analyze this correction factor and see if it's significant or not. Well, the kappa for the animal, so let me get rid of this. It turns out I didn't need this here. The kappa is going to be the thermal conductivity of the tissue, which is approximately the thermal conductivity of water, which is 0.6. But the kappa fur, I'm going to divide these two, is really, what's fur? Fur is a bunch of hairs trapping air between them. Most of the space is actually air. The main purpose of the fur is to just trap air, keep it stationary, so that then you can have thermal gradient through the air. So this is really close to the same as the thermal conductivity of the air. And that we know is 0.026. So the ratio is actually 23. Thermal conductivity of water is 23 times the thermal conductivity of air. So if we can put this layer of air, stationary air, on the outside of the animal, then we win. You might ask, why out here don't you have the stationary layer of air? Well, we're assuming that there's a breeze or something that at the surface of the fur, the air is well mixed and it's at a constant temperature. But inside the fur, the air is trapped and you can have thermal gradients. Okay, so that means this extra term has a factor of 23 right here. It gets multiplied by 2, so you get 46 times delta over L. 1 plus, that's the extra term, is 46 delta over L. It's going to be big compared to 1, unless delta is really small. Let's take a realistic case. Let's say delta, the layer of the thick fur, is a tenth of the size of the animal. So if we have delta over L is equal to 1/10, then this extra term is 1 plus 46 divided by 10, or 4.6. So it's 5.6 times the result that we got without fur. We had 5.2 degrees without fur, and if we multiply that by 5.6, we get the temperature at the center is going to equal the temperature of the surroundings plus 5.2 degrees times 5.6 comes out to be 29 degrees C. So we found a way to keep the animal warm inside. And in fact, if you want it even warmer, if you want it to be 37, because it lives in the Arctic at freezing temperatures, you just make the fur a little thicker. Arctic hares have long fur. So we found a way now we can get some insight into how thick fur should be in order to keep the temperature fixed. Finally, we also want to just say a little bit about the temperature distribution itself. Temperature, L plus delta, minus L, minus delta. Outside, your temperature distribution is going to be, let me make sure I got what I'm doing here. It goes up. Outside, it's like this. This is the surroundings. Now, you're going to have a linear term going as x inside. And since it's absolute value, it goes up over here. And then inside here, it's going to be a parabola. It'll probably be a very narrow parabola. So now the temperature distribution looks something like this. And you see that you've made the actual tissue at a much more uniform temperature. You can put numbers into these values, and you can actually quantitatively analyze this. So you have two advantages. First of all, you've made the temperature at the center even higher. And second of all, you've made the temperature within the tissue more uniform. Most of the temperature drop is coming across the fur. So fur can be a really useful thing. All right, so there is a much more complicated example of how you can use the heat equation to analyze the temperature distribution within an animal. One thing people use this heat equation for is they'll use it to try to analyze, say you're applying heat to treat a tumor, and you want to know what the exact heat temperature distribution is within the body. You want to try to localize it around the tumor, you'd solve your heat equation. All right, a couple more things and we'll be done. Let me erase all this. All righty. I want to make some general comments. First of all, I want to tell you what the bioheat equation is. This is the equation people are using to analyze real tissue. Well, the change in temperature with respect to time is equal to a conduction term, d squared t dx squared, conduction. That's the heat equation. Plus, we have metabolism. So far, this is exactly what we've already done. But if you're really trying to analyze the temperature distribution within our body, you really can't ignore the fact that there's blood flowing. And the blood will flow in, say you're heating up an area in the arm, the blood will flow into the arm, the blood will heat up because your arm's heated up, and then the flowing blood will carry that heat down by convection, carrying the heat through the bloodstream to other parts of the body. So if you really want to analyze this, you've got to realize that there's heat being lost to the blood. Temperature minus temperature of the blood. Well, this is some parameter that depends on the amount of blood flow, how much blood there is, those kind of properties. And that's really a convection term. When you include that, you have the bioheat equation. And either blood is going to be a constant temperature if it's a small localized area of heating, or you'll have to have a whole other analysis to figure out the temperature of the blood. This is the equation people will often analyze. You can also add additional terms. For instance, if you're applying a changing electromagnetic field as the source of the heat, you have the source term in this equation. Now, what happens if instead of dealing with a one-dimensional tissue, we're actually dealing with 3 dimensions? In 3 dimensions, this changes. So a 3D case, 3D is going to look like this. The T temperature with respect to time is D, and now each one of these terms is going to have, each direction is going to have a term like this. So you have another temperature second derivative with respect to y squared, and you have another temperature second derivative with respect to z squared, plus r star over c star, none of that changes, minus w t minus t blood. W might have some sort of directional values, could get complicated. But the key is you have this expression. If you have really a 3-dimensional model where heat can go in any direction, x, y, z. This thing, the collection of second derivatives, is sometimes called the Laplacian. And is given the symbol del squared. So this becomes dt, t little t, equals d del squared temperature plus the other 2 terms. That's how you often see it written in 3 dimensions. So we're not going to be doing 3-dimensional differential equations in this class. I wanted you to see it in case you run into this when you're reading the literature. Now, if this was not biological tissue, but this was just heat in a rock or in a piece of metal, this becomes dt d little t equals diffusion constant del squared t in 3 dimensions. This is really the 3-dimensional heat equation or diffusion equation when there's no sources. And finally, if you're in steady state, the temperature distribution change with time goes to 0. You can cancel out the d, so steady state, this gives you del squared t equal to 0. This has a name. It's sometimes called Laplace's equation. So if you want to spend a lot of time studying heat conduction in materials, you'd spend a lot of time either solving the diffusion equation, or if you're looking at steady state problems, solving Laplace's equation. It's when you have x, y, and z, it's not quite as simple. It's just setting the second derivative to 0. So that is a little bit about the bioheat equation. Next class, we will talk about diffusion itself, diffusion of molecules, and we will talk a little bit about the homework, which then you can get a start on. Let's do a week from Friday. Okay, it's been a pleasure. Empty room. I will talk to you all on Friday.